Okay, it's 9:40, so welcome back again. So let's get started. Quiz 5's out tomorrow, so do Saturday night as usual. Part 2 of homework 2 is also due this coming Sunday. How many of you did something with part 1? Okay, so the rest of you, I would get in the habit of doing these. Just letting you know they're really good for feedback. Any questions before we get started?
Can you go over the difference between a substring and a subsequence? I was having trouble understanding that.
Yeah, so what's a substring?
Subsection of a string.
Yeah, so it's essentially, so just as for a formal definition, I think it says on the homework actually, but substring is a continuous subsequence. And you think, okay, why are you defining substring in terms of subsequence? So when I get to subsequence, all that means is that all of the indices that I'm currently looking at are one right after the other. There's no gaps in between. So a subsequence is, so if we have sequence A1, draw A, right? A1, A2, up to AN. Subsequence is a list of indices I1, I2, let's just say there are K of them, such that, actually the sequence doesn't matter, but the first one better be at least the first one over here, so at least one, but then strictly less for every intermediate one, and IK better be less than. So what it is you just pick a certain number of entries from this sequence, so like a whole string, but they don't have to be one right after the other here. Okay, so for substring, each one of these is exactly one more than the previous one. That's the only difference. Any other questions?
So just to make sure I'm getting this, a concatenation of A1 through A5, A2 and A4 is a subsequence of that concatenation, is that correct?
So let's just say you have a string A1, A2, A3, A4, A5.
Yes.
So what were we saying?
Is A2, A4 a subsequence of that string?
A2, A3, A4, or A2, those two characters?
Just A2 and A4, not
Yeah.
A3.
So A2, A4, that's a subsequence,
Okay.
but not a substring. But if we instead say A2, A3, A4, that's a subsequence and a substring.
Okay.
There is no substring that's not a subsequence. So every substring is a subsequence, but not every subsequence is a substring. Any other questions? Okay. So what was the major thing we talked about in lecture last week? Pumping lemma. So it's strange that this is probably everyone's least favorite part, but it's my favorite part. So it's quite weird. But so yeah, we talked about this thing called pumping lemma. So what in the world does that have to do with anything? What does it help us do? Yeah, so it aids us in proving that a language is not regular. Does it prove directly that a language is not regular? No, what does it do? Yeah, so something with contradiction, but what does the lemma actually say something about?
Properties a regular language must have.
Right, so it says if you have a regular language, then you have some certain properties of the strings in the language. So like when we talked about regular expressions, we talked about describing the strings in the language, but this is a way of describing the structure of the strings in the language. So let's look at a regular language L. And so what does the pumping lemma actually say? Well, let's think about how we were able to prove this. Well, it was some kind of repetition behavior, right? And what repetition of what?
A sequence of states.
Yeah, a sequence of states. So since it's regular, we know there's a DFA for it. If we feed a long enough string, it will have to repeat a state, no matter what. But what other property of the strings did we want to look at? Well, we had to repeat a state, but also what did we have to guarantee? I think someone said it. Something about acceptance. Did we have to accept that string? Yeah, we had to accept that string. And the reasoning is, if we went, say, around that loop one more time, and then went to the same accept state, then we have another string that is in the language of the DFA. But if we can show, via the pumping lemma, that it's not in the language that we want, then that DFA can't possibly work for that language. Because that DFA had to accept that string, but it can't be in the language that we want. And that's the essential idea. So, I should use a different pen. Is the red okay? All right. Every other pen is terrible, except this one. So, there exists a constant P. So the pumping lemma says, if you have a regular language, you have a constant P, such that, well, I gotta look again at the strings that are in the language and have length at least this number, which is the formal way of saying long enough, right? I need to have this repetitions behavior. I don't know what P is, but it's just some constant, such that for all W in L, and the length of W is at least P. So this just means we got to get that repetition in the corresponding DFA, even though we're not talking about the DFA directly. And we got to go to the accept state, even though we're not talking about the DFA. But what does this actually say? Once we get a string like this, what can we say about this string? Yeah, it repeats a certain sequence, but what does that tell me about the string itself? Could I say anything about other strings in the language? Yeah, I can think about going around that loop again, right? But what does that mean corresponds to this string? It means putting another part, something in the middle of that string again, right? I have this part that takes me to this repeating state. I have a way of getting around to the same state. Well, if I went around again, that just means putting another extra copy of something back into the string, right? So it tells me about other strings in the language once I have a string like this. Well, if we look back at our diagram for that, if we have a start state, some repeating state, and some final state, a lot of students get confused. All three of these states could be the same state. I'm just drawing them differently. Well, if this was the repeating state, there is a way to go out and come back. And I need to accept the string because I said it was in the language. So there's some way to get from the start state to that repeating state, and from that repeating state to some accept state. Well, if we call the substring on each of these parts a certain name called X for the part that takes me to that state, the repeating part Y, and the part that takes me from the repeating state to this accept state Z or Z, then what can I say about W first of all? In terms of X, Y, and Z.
W is equal to X, Y, Z.
Yeah, W is equal to X, Y, Z. But do I need to figure out what combination of X, Y, and Z it is? Does that have to work for every combination of X, Y, and Z or just some? Is there some decomposition that works, or do I have to check every single one here? I think, well, I only need to check one, because I only need one way to go around this loop to get to the accept state. So there is a way to write W as X, Y, Z, such that And then we get to our three statements. Well, what does this tell me? This tells me that no matter how many times you go around that loop, how many number of Y's that I read, and then I read a Z afterward, I stay in the language. Well, how do I write that formally? Well, if I read X and any number of copy of Y's, Y to the I, so any number of copies of Y, and then I read a Z afterward, what do I have to know about this string?
In the language.
It's in the language, yeah. For how many I's? All I or just some I?
I read 0.
For all I at least 0, yes. Right? I only need one decomposition in this case for the pumping lemma, but I need every I to work here. But what are the other two conditions that we must have?
Length of x, y is greater than
Which, oh, what is it?
length of x, y is greater than or equal to b.
Not greater than or equal to.
Or
Less than or equal to p. So let's see why that is. Why? Humor in 940. So why is x, y less than or equal to p here? Well, let's see. I said that this works for every string of length at least p. Every single one. That's also in the language. So does it work for the strings of length exactly p? Yeah, it has to. I said at least p here. So consider a string of length p that's in the language. Well, it has to have something like this. So that must mean that a repetition must have occurred, right? A repetition must have occurred because I must have a situation like this. So I know there's at least one repetition in the first p characters. If I choose a longer string, there may be more repetitions. But I know that the first repetition occurs within the first p characters. And that's all I need, right? That's all it's really saying right here. There's some repetition in the first p characters. That's all it's really saying. Okay, what was that second condition then?
y is greater.
Yeah, so the length of y is at least 1, or another way to write that is y is not empty. So why do we want that condition? Well, what if y were empty? What does that tell me here? With this third condition. It tells me, insert as many copies of the empty string as you want. Am I going to get any other string? No, I'm not going to get any other string. So by requiring this, it relates to the diagram, but more importantly, it gets me other strings in the language. It describes other strings. Yeah.
Is there a reason why you described the third one first, or you put the third one down first?
Because well, the way it's commonly written is this way. I could write these in any order I wanted to, but this one related to the actual intuition as to why this is true, the actual diagram. But the way it's commonly written is this. I didn't want to confuse the ordering. I would have written this one first, but this is how it's actually done in the book. And we did a lecture. Any other questions about this? Okay, well, let's start proving things that are to be not regular. So I claim that this language is not regular. So what is this language? It's strings that have zeros, ones, and twos in them, such that zeros are followed by ones, followed by twos, and there's the same number of zeros, ones, and twos. Okay, so the one we talked about in class was zeros again, ones again, but now I'm adding a two again on it. Okay, well, I claim this is not regular, so how am I going to go about proving that? Well, yeah, let's suppose it is regular, because just by saying that, I can't apply this lemma at all, because it only says something about regular languages. But if I suppose to the contrary that it were regular, then I could say something. So suppose L1 were regular. Okay? Well, let's see. How am I going to go about from here? Yeah, there exists a constant p, yeah. So exists a constant p for L1. Okay, so that's pretty easy. But how do I go about from here?
Pick a number.
Yeah, I gotta pick a string. Well, why do I want to pick one string instead of check every single one? Well, it says here, every single string in the language that's long enough will be able to be pumped. But if I can show you one example that can't be pumped, then I know that language can't be regular, because it would have satisfied for all, but I just showed you a counterexample. So that's why I only need to show you one counterexample. So let's pick a string. So we gotta choose some W. So what W should I pick?
0 to p.
Okay, so that seems like a good idea. So remember, it has to be in the language, and it has to be at length at least p. It has to be long enough. So the suggestion was 0 to p, 1 to p, 2 to p. Is that in the language? Yeah, it's zeros followed by ones followed by twos in the same number of each. It has a length at least p. Yeah, it has like 3p, so definitely at least p. So we're good in picking this string. It may not lead to a contradiction, but it's not immediately wrong here. Okay, so now what am I gonna do?
Break it up into X, Y, and Z.
Yeah, so I gotta show breaking up into 3 parts. Only one way to break it up, or do I need to show every way it doesn't work?
Just
One or all of them? I think I need to show all of them. Wait, and you say, you only need to show one right here. Why do you have to do all of them over here? Well, it says, for every string, there is some way to be able to pump the string. Here, I want to show you that this string, no matter how you could possibly think of splitting it up, it won't be pumpable. Okay? So I need to show every possible decomposition. Oh boy, every one. How am I going to do that? Can I make this a lot easier for me? And you guys? Are there some kind of cases I can observe, or is there only one case, or can I observe anything about this, or what?
So if you show that if you break it into X, Y, and Z, and then you have Y is equal to, or I is equal to 0, if you show that that's equal to 0, can we say that since you can't bump it if it's 0, no matter the higher you go, like it
But
is.
I need to show every breakup into X, Y, Z. How do I know what X, Y, and Z are going to be first? Well, let's see. What does this first condition tell me? X, Y's length is at most p. Is X, Y a prefix of the string? Oh, okay. Well, what does that tell me about the string over there? What are the first p characters? Zeros. Oh, what does that tell me about X and Y? They're all zeros. So I don't even need to worry about X and Y having any ones or any twos. Okay, so let's see. So I know X is going to be some number of zeros. Well, again, I got to treat every possible case. So let's just say it has some number of zeros. So let's say A. And we know that A is at least 0, although we won't use that fact here. Again, I know Y consists of zeros, but it may be a completely different number of zeros than X, right? So let's just say that it is B zeros. But what do I know about B here?
at least one.
It is at least 1 because of the second condition, because Y's length is at least 1. Good. Well, what do I know about Z? Well, I think it has to be everything else, right? Because Z is the rest of the string after X and Y. So, well, let's see. I started with P zeros. I took away A for the X part. I took away B of them for the Y part. So I think I have P minus A minus B zeros left. And all of the ones and all of the twos. All of the ones, all of the twos. So what do I need to do now? I'm treating every single possible case, but how do I show that I can get something that is accepted by a possible DSA, but is not in the language that I want? Well, I gotta go around that looping part again, right? Well, what does that correspond to doing here? I gotta pump y either up or down, right? I gotta go around that loop not equal to 1 number of times, right? Because 1 is the original string and that's in the language. I want something that's not in the language. So any value of I that you think would be a good one? It'll turn out every single one other than 1 works, but is there a particular one? 2, okay, so that'll work. So let's just choose, I know it'll work, but let's just say, I don't know if this will work, let's just try it, okay? Sometimes this won't actually lead to a contradiction, but let's just choose it anyway. Well, let's see, what does that mean? That means going, having y be pumped in an extra time. So I have 2 copies of y. Well, what does that mean? That means I have a copy of x, so I'm just going to copy my x down. I have 2 copies of y, so I'm just going to write 0 to the b twice. And then z, which is the rest of this. So 0, p minus a minus b, 1 to the p, 2 to the b. Okay? Well, let's simplify this. So how many zeros am I going to have left? Well, let's see. I think this minus a and this a are going to cancel. So those a's are going to cancel. Oh, and I think the same thing about one of the b's with this b. So those b's are going to cancel. So how many zeros do I have left? P plus b, yeah. So p plus b. And I didn't touch the 1s or the 2s, so this is what I have. Okay? Well, now let's ask the question, is this in the language or not? What's the only possible way this could be in the language? Well, let's just go through every single step. Well, if it's in the language, then this number better be equal to both of these. So this implies p plus b is equal to p. Oh, but then if we just subtract p on both sides, this implies b equals 0. But we have a contradiction because we just said b is at least 1. So what's my conclusion? It's not in the language, right? So this is not in L1. And so what can I conclude overall? It's not regular because I said that it works for all I at least 0 that you stay in the language, but I just found an example of I for what you get out of the language. So I can only conclude from this L1 is not regular. And just a general rule of thumb, if you have a language that consists of strings like this where a run of a certain character depends on the length of another run like this, so like the run of zeros depends on the length of the number of 1s and the number of 2s, then it's probably not going to be regular. Not always, but that's generally what happens. Any questions about that? All right, so let's do the second one. And so it's just a very slight modification. So instead of having equal numbers of zeros, 1s, and 2s, I have 3 times as many zeros as 2s and twice as many 1s as 2s. Okay? So I think we know how to do this part. Suppose L1 prime were regular, there's a constant P for L, 1 prime, but then this part's going to change, right? So what string should I choose for this one? Or do you think would be a good choice? What do you think would be a good choice? Another good rule of thumb here. If you see an N up there, substitute P for N. That's it generally works, not always, but it generally works. So what do you think would be a good string for this? The 0 to 3p, 1 to 2p, 2 to 3p. So I should say those two same things over here. So choose W to be 0 to 3p, 1 to 2p, not 1 again, 2 to p. And I think our lives are going to be even easier here. So let's see. So what's the breakup going to look like here? Is the x part going to change in terms of what I'm writing? Well, it's still going to be all zeros, right? Right. So x is still going to be all zeros. So some number of zeros. Again, I don't know. Is y still going to be all zeros? Yeah, because I have 3p zeros and I have length at most p for x and y, so I'm definitely going to have some left over. So 0 to b again with b at least 1. And again, I think z is going to be the rest of the string. Well, let's see. So z is going to be 3p minus a minus b, 0 is left. 1 to the 2p, 2 to the p. Okay. Well, let's see. What I should I pick this time? What's that? 4 works. Actually, in this case, every value other than 1 will still work. So let's do 4. That'll be fine here. Yeah, it'll work here. So let's choose I equals 4. So x, y to the 4, z. So that is just the x part, 0 to the a. The y part 4 times, so I'm just going to shorten that by saying 4b in the exponent instead of 4 copies of 0 to b. And the z part, which is just 3p minus a minus b, 1 to the 2p, 2 to the p. Well, let's simplify this. The a parts are going to cancel, and one of the b's is going to cancel with this b. So I have 3b left. So how many zeros am I going to have left?
3p plus 3b.
Yeah, 3p plus 3b. Good. I didn't touch the 1s and the 2s. So what's the only way this string could be in the language? Well, the only way it could be in the language is if 3 times this number, p, is equal to this number, because that's what I have up here. 3 times the number of 2's is equal to the number of zeros. So this must mean that 3p plus 3b, so this implies, is equal to 3 times p. And I think we can get the contradiction now. So what does this tell me right here? Well, this implies b is 0 again. So b is 0, which obviously can't happen. So what can I conclude from all this? At 1 time's not regular either. Okay. Okay. Any questions on that? Okay, so now let's do one that's kind of different, but it's really cool in a couple ways, as we'll see in a second. So this language only has zeros in it, so it makes our lives a little easier. But now I'm saying that the number of zeros is a perfect square. Okay, so the empty string's in there, a single zero's in there, 4 zeros are in there, 9 zeros are in there, etc. Right? And I claim that this is not regular. Okay, so how am I going to go about proving this? So how should I start this off again? Let's assume it's regular again. So assume. So I'm rewriting it here and not here because the ideas are going to be slightly different. So assume L2 is regular, then I think we can all agree that there exists a constant P for L. Okay? And it's just the same as before. So now, I gotta pick a string in the language, right? That has length at least P and is obviously in the language. So any choice of string. So someone on the midterm, I guarantee if we have this question, would go this. Is that a good string to pick? It has length at least P. Is it in the language?
Oh, I don't know, right?
Not necessarily, right? I don't know if P is going to be a perfect square, right? I don't know. It may be, but I can't guarantee that. Is there a way I can guarantee this really easily? What? 2 times P? Oh, P squared, you mean? Yeah. Okay, well, let's do P squared. Well, that definitely has length at least P. Is it in the language, though? Yeah, I think so, because it's some integer squared. And some integer squared is a perfect square. So I know that this is in the language, too. Okay? Let's see. What does the decompositions look like? What is the x bar going to be, for example? I think it's going to be all zeros. I'm going on a hunch right here. I think it's going to be all zeros because there are only zeros in the string. So that's why working with unary, this is what's called unary, languages are a lot easier because there are only one character in the language. So it makes our lives a little bit easier. So let's say, again, x has A zeros, y has B zeros, and z has the rest of the string. Well, let's see. I started off with P squared zeros. I took away A, I took away B of them. So I think I have P squared minus A minus B left. Okay? So those are all my decompositions. And obviously, B is at least 1. As always. So now, again, I gotta choose the value of I such that the string becomes out of the language. So you guys suggested the last two, so I'm gonna suggest one now. It turns out I think every single other value other than 1 also works, but it requires a little bit more careful analysis than this one. So this is the easiest one that I know of. Okay, so let's just choose I equals 2. So let's pick x, y squared z again. So what do you think this string as a result is going to be? Well, I'm inserting another B zeros into the original string, so how many zeros am I going to have total? P squared plus B, right? So we can make this a little bit clearer. P squared plus B. So what's the only way that this string could be in the language? Yeah, the only possible way is if P squared plus B is a perfect square. That's the only possible way. But the sad part is this doesn't immediately tell me, like, over here, okay, yeah, B is not 0, right? That's a contradiction. But here, B could be positive, well, it has to be positive, and it still could be a perfect square. It doesn't immediately tell me. So let's just try to see what perfect squares could it possibly be equal to. Well, could it be equal to P squared? Could P squared plus B be equal to P squared? No, and why is that? Yeah, B can't be 0. So I know that P squared is strictly less than P p squared plus b, whatever it is. And this inequality comes from the fact that b is not 0. Okay, so that's immediately obvious. But it may be equal to some other perfect square, right? Like maybe the next one, right? So let's just see, what's the next perfect square after p squared?
This one's
P plus 1 squared. So let's go back to our, I don't know, middle school days, and then let's figure out what this value is. So what is p plus 1 squared? Well, let's just FOIL it out. Well, that's just p squared plus p plus another p. So I have 2p here, and then plus 1 at the end. Well, let's just see. This value may be equal to this. I don't know. It may be equal to the next perfect square. But it may be helpful to figure out what's the largest possible value this could take on. So what is the largest value that this could take on? P squared, I think, is a fixed value. That's never going to change because I set it up that way. What's the largest value that B could be? P minus 1, or could it be equal to P? Yeah, there's nothing that says over here that X had to be non-empty. Y could be all P characters possible. Okay, so I think this tells me that this is less than or equal to P squared plus P. That's the largest possible value it can take on. What do I know about P squared plus P versus this one? Well, I have an extra P and an extra 1 in here. So I know that this value is going to be less than this one. But is it a strict inequality or a possibly equal inequality? Could this be equal to this? No, and why is that? I think it's because of this plus 1 at the end, right? Because even if P, so if P were non-zero, 2P will take over and it'll be larger no matter what. If P happened to be 0, then this is 0 and this is 1. So I think this can't be equal to this. Okay, let's see. So this is the length of the string that I made, and this is the largest value that it could take on. It's not equal to this one, the perfect square. It's not equal to this perfect square, and it's strictly in between them. Is it a perfect square? No, because if it were, it would have been equal to a perfect square, but I just asked, what is the next one? There can't be any in the middle, okay? So this tells me that P squared plus B cannot be a perfect square. And then what can I conclude from this? It's not language, obviously, so x, y squared z is not in, I call it L2. And then what can I conclude from that statement? I think L2 can't be right. So L2 is not right. Okay. So it's really nice to, well, nice in a sense, to say that no DFAs can recognize perfect square length strings because we were able to show that through the pumping lemma, we can get a string that is strictly between two consecutive perfect squares. And so therefore can't be equal to either one of them, and therefore is out of language. Okay? Any questions about that? So let's do an even cooler one, in my opinion. So I'll rinse this part. And so it's starting to creep on us that DFAs aren't really that powerful, in a sense. That there are a lot of languages that we are interested in, but we can't build DFAs for. So 0 to the n is a prime number. Okay, and I want to show that this is not regular, and so we go about this usual way. Assume L3 is regular, then there exists a constant P for L3. Let's see, oh, that should be L2. Okay, so this just proceeds as usual. Every single non-regular proof, except for, like, say, the last one, is going to start with this way. You assume it's regular, then you know that there's a constant P for L. Make a string in the language and long enough, pick an I, and then show that it's not in the language anymore. So now I got to choose some W that's in the language and length at least P. So again, a student might go 0 to P. P stands for prime, and so therefore this is in the language. What's wrong with that? P might not be prime. It may be, but I can't guarantee it is. Is there a way that I can guarantee a prime larger than this? Has anyone heard of the infinitely many primes proof? So there's a proof by Euclid that shows that there are infinitely many primes. So can I guarantee that there's a prime at least P? Yeah, because P is a finite value, there can't be infinitely many things less than it, and at least 0. So there must be a prime larger than it. So let's pick that prime. So pick, so before this, I'm going to say pick any prime, what's a good name for a prime that's not P? R, let's say. R, at least P. But I'm gonna add a little bit to this, and it'll make our proof at the end a lot easier, and you'll see why in a second. I'm gonna make it at least P plus 2. Again, there is a prime larger than P plus 2, just like there was one at least P. And I'm gonna choose a string through the R. So this definitely has length at least P, and is in the language because R is prime. Okay? So let's do our decompositions again. In this case, it actually won't matter what the decompositions are. Because let's think about the decompositions. Well, let's think. The only thing that I really want here is the length of the prime, the length of the string that I'm going to make to not be prime, because I don't want it to be in the language anymore. Well, let's see. Let's pick, let's just look at x, y to the I, z in general. And then we'll decide on a value of I for that works. Well, let's see. Do I know the length of z here? Well, what's the, let's just look at, so this is x, y, z, obviously. Do I know anything about the length of x, y by itself? It's less than or equal to p. So what can I know about the length of z by itself? It's at least 2, right? Because the largest this could possibly be is p, and so this must be at least 2 by this. Okay, so that'll come back to help us in a second. So we know from this that the length of z is at least 2. Okay. What does that tell me about the length of xz? Can x be empty? Yes. What can't be empty? Y can't be empty. X can be empty. So this only really tells me that its also length is at least 2. Okay? It's just knowing that x can't be empty. Okay, well, let's see. So now let's look at x, y to the I z. Well, let's look at its length, because I'm only concerned about the length now. I'm not concerned about the string anymore. Well, I think we can split this up into two parts. The part that involves x and z by itself, and the part that involves y by itself. So I think this is equal to x z's length plus the length of y to the i's length. Right? It's just splitting it up into two parts. No problem there. Oh yeah, that's what I was trying to do. Okay. Well, I think we can simplify this part a little bit. Can I move this I down to here? I think so, because whatever y's length is, this is just I times whatever y's length is, right? Because it's just I copies of y. So I think that this is just I times the length of y by itself. Okay, well, let's see. Just trying to think. Oh yeah, that's exactly what I wanted. Okay, well, I want to pick I such that this number is not prime anymore. Okay? Well, how am I going to do that? Something you might try is, well, is xz an integer I can choose? The length of xz. Is that an integer? Yeah. Could I put that in the value of I? Yeah, it is some integer. I don't know the exact value, like over here where it's like 4 and 2, but I know it's some integer. Let's try that. So here I'm choosing I equals 2. I equals the length of xz. So this is just xz plus length plus length of xz again times the length of y. Okay? Well, let's see. Well, I think that this is just, if I factor this xz length, what does that turn into? I know it's in both of them. Let's just factor it out. So this is just xz times what? Well, I took this out, so I have a 1 left. Divided it out. But what do I have over here? Well, I took an xz out. I think I just have the length of y left over. So this is just the length of y. What is this length? Length at least 2. What about this one? At least 2, right? Because y's length is at least 1. So I have a number that's divisible by at least 2 numbers that are length at least 2. So what can I conclude about this number? It can't be prime because it's divisible by something that has length that is at least 2. And the definition of prime is both that the number is exactly 1 or that number itself. It can't be any other factor. But I just factored it by 2 things that are not that number and not 1. So what can I conclude from this? This is not prime. So what can I conclude about the whole thing? It's not regular because, I should say that from this, I can conclude that x, y to the, I guess, y to the I have to find what I there. X, y to the I, z is not in L3. And then from that, I can conclude L3 is not there. So this whole example was to demonstrate that not only can you look at the general case, but you can also substitute I to be not just a fixed integer that we know. It could just be whatever the decomposition is. at least one I works, then I can prove that it's not right there. Okay? So, any questions about that? I encourage you to look at this one again, because it is a little bit convoluted, but once you see that you can substitute I to be any value you like, you can actually get the properties that you want. Any questions about any of this? All right, I'll see you next week.
Do you have a role in these measurements?